Hello again. So, in this lecture will probably be shorter than the last one, but in this particular one, we just want to talk about how we're going to convert different types of equations from one coordinate system to another, and then talk about a couple of graphing problems that I would like you to be able to do. Nothing horribly complicated, just a couple of standard graphing problems in polar that I would like you to know how to do. Okay, so the point of these exercises of converting one equation to another is the idea behind, okay, does the equation look better in a rectangular form or does the equation look better in a polar form? So let's just do this one in this particular case. So the first one, we've got the equation x equals 5. Okay, so to convert these from rectangular to polar, we need to remember our polar conversion formulas. I'm going to write all of them down over here to the side. We remember we had x squared plus y squared equals r squared. We have tangent of theta equals y over x. We have, what else did we have? We had x equals r cosine theta and y equals r sine theta. Okay, so let's go over to this one. Rectangular to polar. Well, one of the things I notice is all I have is a single x here. If I go over to the first two equations here that we wrote down, I don't have a single x. Everything that has an x also has a y in it, right? So the only equation that has a single x in it is this one right here. So going back over here, we will write this as r cosine theta, because in polar, that's what x is equal to. Is equal to 5. And in a lot of problems that you're doing of this type, it wants you to solve for the r. Write r as a function of theta, writing r in terms of theta. So to do that in this case, we would divide both sides by cosine of theta and get let's write this down below it, r equals 5 secant theta. Okay, before we go on to the next two, let's just, again, I told you, one of the points of this exercise is to determine, is this equation looking better in rectangular, or does this equation look better in polar? Well, let's think about what the actual graph looks like, okay? They both have to represent, it doesn't matter what coordinate system we're in, the geometric shape that comes about from graphing this in rectangular has to be the same as the geometric shape that comes about graphing this in polar. If I graph this in rectangular, it says that the y can be anything. There is no y there, but the x has to be 5. We get a vertical line. I think we can all agree that this x equals 5 describes the situation, because it says the x coordinate has to be 5, period. Describes the situation better than r equals 5 secant theta. If I look at this and think about graphing it in polar, I don't know what that necessarily looks like off the top of my head. So I think the original x equals 5 equation is a lot better than the r equals 5 secant theta. That's just me. Okay. All right. Let's look at this one. Y equals -4. Again, the only one that has y without the x in it is this one here. So we'll replace the y with r sine theta and get r equals -4 sine theta. Again, if we think about just what the graph looks like, y equals -4 is a horizontal line. Again, I think it's a lot more easily described as the y coordinate has to be -4 than saying the distance that the point is from the origin is -4 times whatever the sine of the angle is that the point makes with the origin. That's a really crazy way to describe a line. So again, it looks like linear functions, equations of lines, look better in rectangular coordinates than they do in polar, at least in my estimation. Let's look at this one, though. X squared plus y squared equals 16. This is kind of the special form, if you will, like I like to think of it, for polar. This one's easily recognizable. If I see x squared plus y squared, I want to replace that with r squared. So right away, I see that the equation got simpler. It had 2 variables in it, now it only has 1. And now we take the square root of both sides, and we get r equals 4. Now let's think about what the graph of this looks like. Well, if you're clever and you remember, this is the equation of a circle. Centered at the origin, radius is 4. The radius was that square root of that number on the other side. And then you get that graph. But look how much more easily this equation is, or this shape is represented in polar. It's a constant in polar. This is not even a function in x and y, right? It doesn't pass vertical line test. However, in polar coordinates, this is a function of theta. You plug in a theta, you always get 4 out because there was no theta to plug in there. So this, in terms of functions of theta, this is a function of theta. It's a constant function. So this is a lot more easily described in polar than it is in rectangular. And this is what I mean by when you're going to get to calculus, you want to be able to recognize forms that are more easily written in polar than they are in rectangular. And usually the rule of thumb is if you're dealing with circles or pieces of circles, you're probably going to want to convert it to polar because it's a lot easier to describe the region in polar than it is to describe the region in rectangular. Let's do a couple more here. These are, again, fairly straightforward because we're just going to want to plug in the different conversions. X is equal to r cosine theta. Y is equal to r sine theta. So we get 4r cosine theta minus 3r sine theta equals 18. And again, in these problems, you're typically going to be asked to solve for r. So in this particular one, we want to factor out the r. Oops, this should have been a theta here, not a sine of y. My apologies. That should have been a sine of theta. So we get 4 cosine theta minus 3 sine theta inside the parentheses, r factored out in front, equals 18. And then to solve for r, we have 18 over 4 cosine theta minus 3 sine theta. Now again, remember that these two things have to represent the exact same shape when you graph them. So the graph of both of these is the exact same line, because 4x minus 3y equals 18 gives you an equation of a line. Notice again, like I was mentioning with the other ones, it's a lot easier to see that this is a line than to see that this is a line. And if you want to be convinced that you really do get the graph of this thing is a line, I'm not going to go through it. I'm going to show you on the calculator just real quick here, but I'm not going to graph it. I just want to show you in case you want to investigate it for yourself. See if I get the calculator open sometime today or not. Let's try it this way. Oh, here it comes. It's just being slow. Very slow. I'm not sure what's taking so long. Okay, here we go. I just want to show you how you can graph things in polar if you're interested, just to see what the graph looks like. Go to mode. Right now, you are in function mode, which basically means you're graphing in rectangular mode. To convert to polar mode, you can go over and select the polar, and it'll change it to polar. Now, if I go back and quit out of this and go to like you were going to graph something, notice that it starts with r equals something instead of y equals something. And if I hit the button that's for x, it'll actually print out a theta. So if you're interested in what the graph of that other equation looked like, you can type in that equation here and graph it and see that you really will get a line. I promise that you'll get a line. Okay. I'll leave that for you to do as practice if you're really, really interested in that. But I just wanted to show you how you can graph in polar on your calculator just for a little bit. We're not going to do much with graphing at all. But again, in calculus, especially in calculus 2, you'll do more things with polar, so you might be interested in doing those graphs so you can actually see what they look like. Okay. All right, so let's go back over here. Here's one. This is a parabola. We know it's a parabola because one of the variables is squared and the other one is not. But again, pretty straightforward. We're going to plug in r cosine theta for x. We'll put in r sine theta for y. And I said y instead of, and wanted to write y instead of the squared. So we get r cosine theta equals r squared sine squared theta over 5. I want to solve this for r. Well, if I solve this for r, I better divide both sides by r. And then I better multiply by 5. And write a better looking 5. And divide by sine squared. So I have r, I just divided by the r, multiply by the 5, divided by the sine squared. So I have r equals 5 cosine of theta, 5 cosine of theta over sine squared theta. Now we're going to be a little bit clever, because we like to be clever. I'm going to rewrite that sine squared as sine times sine, so that I can write this as 5 times cosine theta over sine theta times 1 over sine theta. And the reason why I did this is, of course, that I recognize those two things as different trig functions. The first one is cotangent theta. The second one is cosecant theta. And usually we write the cosecant first and then the cotangent. Mainly because cosecant is alphabetically ahead of cotangent. It's really the only reason why we do it that way. All right, so anyway, there is our equation of the parabola changed to polar. Okay, so let's go the other way. This one asks us to convert from polar to rectangular. And these involve a couple of little tricks here and there, which is why I've got 7 of these here just to illustrate what's going on. First couple are straightforward. R equals 4. Well, again, just to remind ourselves, x squared plus y squared equals r squared. Tangent of theta is y over x. X is equal to r cosine theta. Y equals r sine theta. All right, so r equals 4. Well, I don't have an equation, except for the one that has just cosine of theta or sine of theta in it. I don't have one conversion formula that just has an r, but I do have an r squared. So in this particular case, what I'll do is I'll square both sides. Now, be careful. You don't always want to square both sides, okay? But in this case, squaring both sides works. There's another way to get an r squared, by the way. So just to be careful with that, you don't necessarily always want to square both sides. It's not always what happens, all right? Just watch out for that. But here, we square both sides, we get r squared equals 16. And so we'll get x squared plus y squared that we can put in for the r squared equals 16. So that converted that to polar, and we see again that this is a circle, but the r equals 4 would have been an easier way to describe that circle to begin with. Theta equals pi over 6. Well, I don't have one that's just theta by itself, except for this one. Right? There's no, what I mean by theta by itself is I don't have one that it has a theta but no r, right? The other two on this side have both r and theta together, and this one doesn't even have theta in it at all. So this is the only one that has theta by itself without the r. However, to use this conversion formula, I need tangent of theta. Well, I can get that easily. Let's just take the tangent of both sides. So I get tangent of theta is tangent of pi over 6. And now I can plug in y over x for theta. We take the tangent of pi over 6. That's 1 over root 3. And now if I want to write this in a more familiar form, I can write it as 1 over root 3 times x. And I recognize the theta equals pi over 6 as a line. Y equals that slope times x. That is an equation of a line. All right. Well, this one's even more straightforward. This one says tangent of theta equals 1. It already gave us tangent of theta. Well, we just said in the last problem that tangent of theta is y over x, so I can plug that in immediately and get y equals x. So that one was pretty straightforward. Do the next one here. This one's not bad. It looks worse than it is. Okay. All right, so I have this r equals this 6 over 5 sine theta plus 2 cosine theta. I need conversions. Well, these are the conversion formulas that we have, the ones that are up here in the upper right-hand corner. If I'm going to use conversions that have sine or cosine in them, I need an r multiplied by the sine or by the cosine, right? Well, the easy way to get an r multiplied by the sine and cosine in this case is just to multiply both sides by the denominator here. So r times 5 sine of theta plus 2 cosine of theta equals 6. Now let's distribute the r. So you get 5r sine theta plus 2r cosine theta equals 6. R sine theta is y. R cosine theta is x. So we get the equation 5y plus 2x equals 6. So again, we recognize this is the equation of a line. So the original thing was also the equation of a line, which is probably a little bit more recognizable in the rectangular case than in the polar case. Okay, so let's talk about this one. This one's a little bit trickier. We said that we can get an r squared by squaring, right? And if we get an r squared, we can get an x squared plus y squared. But it's not the only way that you can get an r squared. And in particular, I would not want to get an r squared here by squaring both sides, because if I square over here, I get a mess. I get a cosine squared, I get a sine squared, I get a sine times a cosine when I FOIL. Squaring is a really, really bad idea here, all right? Well, how else can I get an r squared, though? Because I love that conversion formula, r squared equals x squared plus y squared. It's a great conversion formula. Love to use it when I can. So I'd like to be able to see an r squared if I can. However, I really, really don't want to square both sides because that right side will be a mess. But another way to get r squared is simply just to multiply both sides by r, right? R squared is r times r. So another way to get r squared is just to take r times r, multiply both sides by r. Get r squared on this side. Over here we'll get minus 4r cosine theta plus 2r sine theta. And now we're ready to plug in things. R squared is x squared plus y squared. R cosine theta is x. And r sine theta is y. So we get x squared plus y squared equals negative 4x plus 2y. Now you might recognize that as the equation of a circle. And if you remember your college algebra stuff, you probably remember how to do completing the square. I don't expect you to do this part, but I just want to show how we really do see that this is a circle. Move everything to the left. So I need to add 4x and subtract 2y. We still have 0 on the right-hand side. If we complete the square, remember how we complete the square? You divide this coefficient by 2 and square it, so you'll get a plus 4 here. Divide this coefficient by 2 and square it, you'll get a plus 1 here. Of course, to keep things equal, I better add a 4 and add a 1 on the right-hand side. And now we see how this factors. This is x plus 2 squared. This is y minus 1 squared, and this is 5. So what this tells us is that we have a circle centered at the point negative 2, 1. Remember, it's always the opposite signs that are inside here with radius 5. Now again, once you get to here, the part that I've boxed, you can stop. You do not need to do this last part that I just did, all right? When you get to this boxed step, you're fine, okay? I just wanted to show you that we really do have a circle and what that circle would actually look like. Now again, you might not think that this formula that we started with up here, this is our starting formula up here that I just put an asterisk by. You might not think that this formula is nicer than the circle formula that you have in rectangular, but it is, and here's why. Think about the graph of a circle. For rectangular coordinates, a circle does not pass the vertical line test. It's not a function. X is not a function of y is not a function of x. However, this starred equation, r is a function of theta. You plug in one value for theta, you get one value out for r. R is a function of theta. Okay? Which means that you can do function things for this particular equation that you can't do for this particular equation. Makes life a little bit simpler. Again, in general, it's like what I mentioned before. Circular things, circles and pieces of circles, are usually much nicer represented in polar than they are in rectangular. Now, you may not, like I said, you may not think the function form is nicer, but the key word that I just used was function. This is a function. This one is not. Okay, so that circle was actually a function in polar coordinates, where it wasn't in rectangular. All right. This one has the same idea. I love r squared. If I can get me an r squared, I'm going to take me an r squared. Okay? So, but I don't want to get r squared by squaring all the time. In fact, most times you don't want to get r squared by squaring. You want to get r squared by multiplying both sides by r. Okay? R squared equals 4r sine theta. The r squared is x squared plus y squared. And the r sine theta is 4y. And again, we see a circle. And if you really wanted to, you could do the completing the square idea. To give you an idea of what the circle looks like, it would be graphed like this, where this point right here is 4. And it's centered here at 0, 2. Okay. I don't expect you to get the graph of that. I just want to show you what it looks like. Again, if you want to practice with your calculator to see what some of these shapes are, plug them in. Some of them are really kind of cool looking. All right, last one. R equals 3 secant theta tangent theta. Again, really want to get an r squared if I can. But again, I don't want to square both sides because I would get a secant squared, a tangent squared. That's not helpful. I don't have conversion formulas for those. So again, let's square by multiplying, or let's get an r squared by multiplying both sides by r. Okay, that didn't seem to help a lot, but before I do anything else, let's just do some playing around with some pieces here. Well, secant is 1 over cosine, and tangent is sine over cosine. Notice the denominator here is cosine squared. So let's move that to the other side. So we have r squared cosine squared theta equals 3r sine theta. Okay, this is cool because r sine theta is y. What about this piece? Well, okay, well I've got r squared and I have cosine squared. So I can pull off the squared. Now I see r cosine theta, that's x. And r sine theta is y. So I get x squared equals 3y, and I notice that's an equation of a parabola. These give you the types of conversions that I would be expecting you to do from polar to rectangular, doing these kinds of ideas. All right. One last topic. I want you to be able to graph a couple of straightforward polar graphs, just by what the shapes have to be. So here's some polar graph paper, and you should have some of this. I posted it on Moodle. So again, notice that these hash marks for the circles are all a half a unit, right? Here's 1, here's 2, here's 3, here's 4. Your angles are still 15-degree angles each line. So pi over 12, pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2. This one asks you to graph r equals 6. Theta can be anything, but r has to be 6. So again, this says the distance from the pole has to be 6, but theta can be anything. Well, this point is 6 units away from the pole. This point is 6 units away from the pole. This point is 6 units away from the pole. So is this one. And we have a whole bunch of other ones, right? So this, since theta can be anything, this circle is the graph of r equals 6. And in general, if you have r equals a number, as long as that number is, well, actually it can be negative as well. It'll still be a circle. But if you have r equals a constant, that's going to be a circle that you're going to graph. All right, and then the other type of one that's pretty straightforward that I want you to be able to graph is the theta equals negative pi over 4. This says that r can be anything because there are no r's in it, but theta has to be negative pi over 4. Well, negative pi over 4 is down here on this line. Here's your negative pi over 4. Positive r's would go this way, but I said r could be anything, so r could also be negative, so they can also go backwards this way. So you get this line in this case that gives you the theta equals negative pi over 4. That's what the equation gives you as far as the graph. All right, so that practice sheet that I posted on Moodle, I would suggest going through the rest of those problems now, the ones that you would have started after Friday's lecture. And then we have a take-home quiz that'll open up later today. And then that'll be due on Wednesday by 5 o'clock. And as usual, you can email me questions. You can schedule a Zoom meeting with me, whatever you would like. I'm more than happy to help. So anyway, I'll talk to you later.